Hello, this is lesson 15.5, de Broglie wavelength equation and atomic wavelength. Now, this is actually something very similar to something we've already done. Specifically, that was within section 14.4.5 on matter waves. But I did want to just first of all emphasize that these three videos, right here, here, and here, they do a fantastic job of going through everything. So if you haven't watched them, watch those first, and then we'll take a look at some of the class notes. So pause the video, go there, come back. Okay, assuming that you've done that, essentially, again, taking a look is that matter can do sorts of things, such as electron diffraction. Basically, you take a diffraction grating, fire electrons through it, and what you find is that they will actually create a resulting interference pattern. Even if you shoot them through one at a time, you wind up with an interference pattern, which is, well, really quite crazy when you think about it. Now, that eventually led to the fact that electron interaction with matter, unlike other types of radiation used in diffraction studies of materials such as X-rays and neutrons, electrons are charged particles and interact with matter through Coulomb's forces, right? Because Coulomb's law. Right? That means that electrons can be influenced both by positively charged atomic nuclei and the surrounding electrons. And eventually we get to this formula. Now, this is not the formula that's on your formula sheet. It is a variation. P is equal to h over wavelength. And again, we discussed this in section 14.4.5. Right? So, taking a look at just a few examples here. What is the frequency of an electron moving at 2,000 meters per second? Well, if P is equal to lambda over h, now if we are looking for the frequency, we're going to need to take the wavelength of this and use the universal wave equation. Okay, velocity here though is not c. It is 2,000 meters per second. And so P being mv, h over, now the wavelength would just be velocity times frequency, or velocity over frequency would be the wavelength, sorry. What you should see here is that gets you mv squared over h is equal to the frequency. Mass of the electron, 9.11 times 10 to the negative 31 kilograms. The velocity being 2,000 meters per second squared, all divided by h, and we're going to use the standard units here, 6.63 times 10 to the negative 34 joule seconds. And the reason for that is because we've got kilograms and meters, so we're going to do this in seconds to get the frequency, or a frequency of 5.5 times 10 to the 9 hertz. What if this electron is moving in a circular path with a radius of 0.5 meters under the influence of a magnetic field with this strength? Well, the centripetal force that's causing the move in the circle is caused by the magnetic force. And so we've got mv squared over r is equal to qvb, and one of the velocities cancels out. We're looking for the wavelength of the electron, and so we're going to do something a little bit manipulating here, really what we're going to do is we're going to first of all find out the speed of it. And so V is equal to QBR over M. That velocity is therefore where we're using the charge of 1.6 times 10 to the negative 19 coulombs, the magnetic field being 5.3 times 10 to the negative 3 Teslas, the radius being 0.5 meters, all divided by the mass of 9.11 times 10 to the negative 31 kilograms. That velocity is going to be 4.6 times 10 to the 7 meters per second. Now, wavelength being equal to h over momentum, right? Now, again, we're multiplying the mass back into here, and yes, you could have done a direct substitution, solve for the momentum, mv in this case, which would be equal to qbr, and put that in there, and then put that over h. Sometimes it's a little bit easier to see it as two-step equation, but you could have done the direct. 10 to the negative 34, divide that by momentum 9.11 times 10 to the negative 31, and that velocity of 4.6 times 10 to the 7 meters per second gets you a wavelength of 1.6 times 10 to the negative 11 meters. Oh, sorry. This was based on a times 10 to the negative 2. That's a little typo there. My bad. I'm sorry. The numbers work out, but that's 5.3 times 10 to the negative 2. Alright, so let's take a look at our third example here. Calculate the wavelength of a proton accelerated from rest through a potential difference of 900 volts. Well, first of all, we're going to need to figure out what velocity is, and that's by the change in energy, right? Or 1/2 mv squared is equal to q times the voltage, or the velocity is equal to 2qv over m all square rooted. Now, when you solve for that given charge of 1.6 times 10 to the negative 19, 900 volts, and the mass of the electron being 1.67 times 10 to the negative 27, means that this is moving at 4.15 times 10 to the 5 meters per second. And so the wavelength being h over mv. Now, in this particular question, substituting in, trying to find the momentum directly, is a lot more difficult because you're dealing with this v squared. Not one of the v's are canceling out. So doing this as 2 steps is probably preferable. Again, 1.67 times 10 to the negative 27, 4.15 times 10 to the 5. That should generate a wavelength of 9.6 times 10 to the negative 13 meters. Okay, what is the kinetic energy of a proton whose wavelength is the same as a 450 electron volt electron? Well, let's first of all move that 450 electron volts, and let's turn that into joules. Okay, that should get you 7.2 times 10 to the negative 17 joules. And so what we can do is so if that's the kinetic energy of the electron, what we're going to do is we're going to now find the wavelength of that electron, because it's the wavelength of the proton and the electron that are the same. So, given the kinetic energy, we can find the velocity. Okay, or V is equal to what would be 2e over m all square rooted, where the energy is being 7.2 times 10 to the negative 17. So the velocity of the electron is 1.25 times 10 to the 7 meters per second. So the wavelength of the electron being h over mv, again, Planck's constant, mass of the electron, both constants, you should find that wavelength to be 5.78 times 10 to the negative 11 meters. So that is the wavelength of the electron and of the proton. So when we come back to this formula for the proton, V is equal to h over wavelength times velocity, mass. Again, we've got Planck's constant, 6.63 times 10 to the negative 34. All over that wavelength of 5.78 times 10 to the negative 11, multiplied by the mass of 1.67 times 10 to the negative 27. You should find that to be 6868 meters per second. Okay, so we've got the velocity now of that proton. We want to find now the kinetic energy. Well, that's just 1/2 mv squared. Okay, we've got the velocity, so that's equal to 1/2 times 1.67 times 10 to the negative 27 times 6868 squared. Now, that works out to be 3.93 times 10 to the negative 21 joules. Now, if we wanted to turn that into electron volts, we're going to simply divide by 1.6 times 10 to the negative 19. And this works out to 0.025 electron volts. It has a whole lot of less energy at that wavelength. Hopefully that helps. If you got any questions, let me know.